The cosmic microwave background radiation, CMB, represents one of the most profound scientific discoveries of the 20th century, providing compelling evidence for the Big Bang theory and revolutionizing our understanding of the universe's origins. This ancient light pervades the entire cosmos and serves as a direct snapshot of the infant universe when it was merely 380,000 years old. The CMB is essentially the thermal afterglow of the Big Bang itself, allowing astronomers to peer back to nearly the beginning of time. This remarkable cosmic relic has been extensively studied since its accidental discovery in 1964, revealing crucial details about the early universe's conditions, composition, and evolution. Its uniform temperature of approximately 2.7 Kelvin across the entire sky, with only minute variations, provides scientists with a treasure trove of information about cosmic evolution and structure formation. The cosmic microwave background radiation is essentially leftover heat from the Big Bang, or the time when the universe began. According to cosmological theory, the early universe was extremely hot and dense immediately following its inception, undergoing rapid inflation, expansion, and cooling. This primordial radiation that we detect today as the CMB has been stretched and cooled over the past 13.8 billion years as the universe continued to expand. The CMB permeates the entire universe, but remains invisible to the human eye because it is extremely cold, measuring just 2.725 degrees above absolute zero, approximately 270.4 degrees Celsius. Due to this low temperature, its radiation is most prominently detectable in the microwave portion of the electromagnetic spectrum, hence its name. One of the most significant properties of the CMB is its remarkably uniform temperature distribution across the entire sky, exhibiting isotropy with only minuscule variations of about 1 part in 100,000. This high degree of uniformity provides robust support for the Big Bang theory, as it aligns perfectly with theoretical predictions. The CMB also displays a blackbody spectrum, meaning that its intensity at various wavelengths follows a specific pattern consistent with radiation emitted by a perfect blackbody at 2.7 Kelvin. This blackbody characteristic represents another crucial piece of evidence supporting the Big Bang theory, as it indicates that the radiation originated from a thermal equilibrium state in the early universe. The radiation's profile matches exactly what would be expected from a hot body that has cooled down over an extremely long period of time. The cosmic microwave background radiation was officially discovered in 1964 by American radio astronomers Arno Allen Penzias and Robert Woodrow Wilson, while they were working with the Holmdel Horn antenna at Bell Labs in New Jersey. Their discovery occurred essentially by accident when they detected a persistent background noise, an unexplainable hum that emanated uniformly from all directions in the sky. Initially puzzled by this phenomenon, Penzias and Wilson meticulously eliminated all possible sources of interference, even removing pigeons that had nested in the antenna. After exhausting all explanations for the mysterious signal, they ultimately realized they had stumbled upon something of profound cosmological significance. Penzias and Wilson estimated the temperature of this radiation to be approximately 3.5 Kelvin, remarkably close to the currently accepted value of 2.7 Kelvin. Their groundbreaking discovery earned them the 1978 Nobel Prize in Physics. However, an often overlooked fact is that there had been a prior measurement of cosmic background radiation by Andrew McKellar in 1941, who detected an effective temperature of 2.3 Kelvin using CN stellar absorption lines observed by W.S. Adams. Although McKellar did not reference the cosmological implications of his measurement, its significance was recognized much later after the Penzias and Wilson discovery. The cosmic microwave background radiation originated approximately 380,000 years after the Big Bang event that occurred roughly 13.8 billion years ago. In the universe's earliest moments, temperatures were incredibly high, about 273 million degrees above absolute zero, according to NASA. At such extreme temperatures, atoms could not remain intact. They were immediately broken apart into their constituent particles, primarily protons and electrons. This created a dense, opaque plasma where photons, light particles, could not travel freely as they constantly scattered off electrons, similar to light being scattered in a dense fog. As the universe expanded and cooled, it eventually reached a critical temperature threshold of about 3,000 Kelvin, allowing protons and electrons to combine and form neutral hydrogen atoms in a process called recombination. This transformative event fundamentally changed the universe's properties, as photons could suddenly travel freely without being scattered by free electrons. This moment, referred to as decoupling, marks when the universe became transparent to radiation. The light released during this transition is precisely what we observe today as the cosmic microwave background radiation. Initially, this radiation would have been extremely energetic, likely in the gamma ray or X-ray region of the electromagnetic spectrum. However, over the subsequent 13.8 billion years, the expansion of space itself has stretched these light waves, increasing their wavelength and shifting them into the microwave portion of the spectrum through a process known as cosmological redshift. This explains why radiation that began as high-energy light is now detected as microwave radiation with a temperature of just 2.7 Kelvin. The discovery and subsequent detailed mapping of the cosmic microwave background radiation provided decisive evidence favoring the Big Bang theory over its main competitor, the steady-state theory. In the mid-20th century, cosmologists were divided between these two competing models explaining the universe's creation. The steady-state theory, proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle in 1948, suggested that the universe has always existed and continues to maintain the same average density and appearance through infinite time, with matter being continuously created to form new galaxies as the universe expands. In contrast, the Big Bang theory proposed that the universe originated from an extremely hot, dense state in a singular explosive-like event billions of years ago. A critical prediction of the Big Bang model was the existence of residual radiation permeating the entire universe, precisely what was discovered as the CMB. The steady-state theory could not adequately explain the presence of this uniform background radiation coming from all directions in space. The CMB's discovery therefore represented the conclusive evidence that established the Big Bang as the scientifically accepted model of cosmological origins. Since its initial discovery, technologies for observing and measuring the cosmic microwave background radiation have advanced significantly, allowing scientists to extract remarkable amounts of information from this ancient light. Modern space-based telescopes like the Planck mission have created detailed maps of the entire sky, revealing minute temperature fluctuations in the CMB. These tiny variations, at the level of 1 part in 100,000, represent quantum fluctuations in the early universe that eventually grew through gravitational attraction to become the galaxies and large-scale structures we observe today. The CMB has proven invaluable to cosmologists as it enables them to learn about the early universe's formation process. By studying these temperature fluctuations, scientists can determine fundamental cosmological parameters, test theories about cosmic inflation, and measure the relative abundances of normal matter, and dark energy in the universe. In 2014, scientists announced evidence of primordial gravitational waves in the CMB, potentially providing a smoking gun for the theory of cosmic inflation. The rapid expansion of the universe in its first fraction of a second. The cosmic microwave background radiation stands as one of astronomy's most significant discoveries, offering a direct window into the universe's earliest moments. This ubiquitous signal, uniformly distributed across the cosmos with a temperature of 2.7 Kelvin, represents the oldest light in the universe that humans can detect. Its discovery conclusively validated the Big Bang theory, transforming our understanding of cosmic origins and evolution. As observational technologies continue to advance, the CMB continues to yield new insights about the fundamental properties of our universe, from its composition to its geometry and ultimate fate. This ancient radiation, having traveled across space for nearly 14 billion years, continues to illuminate our understanding of cosmic history and remains an active area of research in modern cosmology.